You have looked at this symbol 1,000 times. Nobody has ever told you what it actually does. So here is the truth. It is not a number. It is not an operation. It is a recipe, a one-line instruction that says, do this, then do this, then do this, and stop. That is all a sigma is. And once you see it that way, you will never unsee it. Look at the shape. A big Greek capital sigma in the middle. Underneath, something like k equals 1. On top, a number like 10. And to the right, an expression that uses the letter k. Here is what every piece is for. The letter k is a counter. It has no meaning of its own. The bottom tells the counter where to start. The top tells it where to stop. And the expression on the right is what you do at every step before you move on. Start, plug in, write it down, add 1 to the counter, plug in again. Keep going until the counter hits the top. Then add everything you wrote down. That is the entire machine. Nothing is hidden. Nothing is magic. Let me show you one. Sum from k equals 1 to 5 of k. The counter starts at 1, 1. Counter becomes 2, 2. Counter becomes 3, 3, 4, 5. Stop. Now add them. 1 plus 2 plus 3 plus 4 plus 5 is 15. That is it. The symbol said 15. It just said it in 4 characters instead of 9. It is shorthand. It is compression. The instant you expand it, the mystery evaporates and you are left with grade school addition. Now try something just slightly harder. Sum from k equals 1 to 4 of k squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Add them. 1 plus 4 is 5. 5 plus 9 is 14. 14 plus 16 is 30. The symbol said 30. Watch what happened. The counter walked from 1 to 4, but the thing you wrote down each time was not the counter itself. It was the counter after a rule had been applied. That is the whole point. The summand can be anything you want, any function of k. The letter of the counter does not even matter. You could use I, or j, or n, or the Greek letter mu. The symbol does not care what you call the counter. It only cares that something is walking, and something is being written down at every step. Here is something worth knowing about these finite sums. Sometimes the recipe has a shortcut. The sum from k equals 1 to n of k, for any n you pick, is exactly n times n plus 1 divided by 2. You do not have to walk the counter. You can just plug n in. Try it with n equals 5. 5 times 6 over 2 is 15. The same 15 we just got the long way. There is a shortcut for k squared too, and k cubed, and geometric sums, and alternating sums, and on and on. None of these shortcuts change what the sigma means. They are theorems that sit next to the sigma and say, by the way, if your recipe looks like this, here is the finish line without the walking. The sigma is still the true statement. The closed form is a gift. Now here is where people get scared, and they should not. What if the top of the sigma is not 10 or 100, but infinity? That word panics everyone. It should not. It is still a recipe. It just says keep walking the counter and watch where the running total is heading. If it is heading to a specific number, that number is the answer. If it is running off to nowhere, there is no answer and the sum is said to diverge. Here is one that does something beautiful. Sum from k equals 1 to infinity of 1 over 2 to the k. 1/2 plus 1/4 plus 1/8 plus 1/16. After 4 steps, the running total is 15/16. After 10 steps, it is 1023 over 1024. It is creeping upward, and it is never going to cross 1, and 1 is exactly where it lands. An infinite recipe, a finite answer. Nothing mystical happened. A bound was approached. That is all the word infinity ever means inside a sigma. Now watch this one, because it is going to feel like a trick. Sum from k equals 1 to infinity of 1 over k squared. 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 forever. It converges. That part is not shocking. The terms shrink fast enough. The shocking part is the number it converges to. Pi squared divided by 6. roughly 1.6449, and then more digits after that, none of them repeating, none of them stopping. Stop and feel that for a second. You started with a list of reciprocals of perfect squares. Nothing round, nothing circular, no triangles, no angles. You were just dividing one by the counting numbers after squaring them. And out the other end of an infinite sum falls pi, the constant for circles. This result has a name. It is called the Basel problem. Euler solved it when he was in his 20s, and when he did, he changed how people thought about what a sum could be. Whatever pi really is, it is hiding inside the plain integers, and the sigma is the key that unlocks it. Now forget sigma for a moment. There is a second symbol, and it is the twin, a big Greek capital pi. Same counter underneath, same top, same expression on the right. One rule changes. Where sigma told you to add, pi tells you to multiply. That is the entire difference. The counter still walks. The summand is now called a multiplicand, and at every step you fold it into a running product instead of a running total. The cleanest example is one you already know by another name. The product from k equals 1 to n of k, that is n factorial. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. You have used pi notation your whole life without the symbol. And because I told you about a beautiful sum, here is a beautiful product. Take the product from k equals 1 to infinity of 2k squared divided by 2k minus 1 times 2k plus 1. It sounds ugly. Let me just read the first few factors out loud. 2 times 2 over 1 times 3, 4 times 4 over 3 times 5, 6 times 6 over 5 times 7, 8 times 8 over 7 times 9. Keep going forever. That product converges. It lands on pi divided by 2. You just multiplied a parade of ratios of integers, and out fell pi again. This is the Wallis product, and it is one of the oldest results in analysis that connects integers to the circle. Different recipe, same ghost in the machine. A capital pi, written once, swallowed an infinite process and handed you back half of the most famous constant in mathematics. So now step back from the symbols themselves. The sigma is not doing any math. The pi is not doing any math. They are, both of them, containers. They hold a counter, a start, a stop, and a rule. They are a way of writing an unbounded process on one line of a page. The math is not the symbol. The math is what happens when you unfold the symbol. The symbol is compression. The value is decompression. And the ability to take a process that could run a billion steps or infinite steps and fit it inside a single glyph is not a notational convenience. It is the thing that lets mathematics talk about things it cannot finish writing down. Once you see that, you see them everywhere. Sigma is 2 plus what pi is 2 times. But the pattern does not stop at those two. There is a symbol that takes the maximum over an index. There is a symbol that takes a union over a family of sets. There is a symbol that takes an intersection. There is a symbol for direct sums of vector spaces. Every one of them is the same shape of idea: a counter, a start, a stop, a rule, a way to fold. Once you have internalized the sigma and the pi, you have learned the grammar, not the vocabulary. Every future big operator you meet will feel like a dialect of a language you already speak.